In this session, we will discuss about correlation between time and frequency response. We have studied about the time domain specifications and also about the frequency domain specifications, and we will find the correlation between these two quantities. For that, we are taking the magnitude of the closed loop system as m equal to modulus of m of j omega equal to 1 divided by square root 1 minus u square all square plus 2 epsilon u whole square. And this is the magnitude in the case of frequency domain system, that is equal to 1 divided by square root 1 minus u square all square plus 2 epsilon u all square. Similarly, we will get the phase of the closed loop function as alpha is equal to angle of m of j omega, that is equal to, here phase will be obtained by taking the imaginary term divided by real term, that is equal to minus. Since it comes in the denominator side, there will associate a minus sign, so minus tan inverse 2 epsilon u divided by 1 minus u square. So these are the magnitude and the phase of the closed loop system in the case of frequency domain system, frequency domain representation. And here when we are taking the magnitude and phase angle characteristics for normalized frequencies u, the certain values of epsilon, for certain values of epsilon we will get different curves for this m and alpha, and figure shows the magnitude plot and phase plot corresponding to different values of epsilon. See here, there are different plots for m with respect to u, and here first is epsilon will be equal to epsilon 1, that will be less than 0.707, and this may be for epsilon greater than 0.707. So this is 0.707 means 1 by root 2. So we are taking for two conditions, when epsilon value will be less than 0.707 and epsilon value will be greater than 0.707. So the curves of m with respect to u, see here m is a function of u alone. Here in this equation m is a function of u and epsilon. So we will plot m with respect to u for taking a certain value of epsilon. So here we are taking two conditions and we got the two cases, and in first case you can see that for epsilon less than 0.707 there is a resonant peak occurring here. So the corresponding frequency is resonant frequency, that is represented as UR. In this case there is no resonant peak like the previous one. So it's in the second case the value maximum value is 1 and then it decreases. Similarly in the first case, first the resonant peak will occur here and then it decreases like this. So in the case of a phase angle plot, the phase angle changes from 0 and then decreases to some value. For any value of epsilon equal to epsilon 1, the phase plot will be looking like this. So we can say that the peak value of the magnitude is the resonant peak MR. At this frequency, the slope of the magnitude curve is 0. And the frequency corresponding to resonant peak will be is equal to UR, and which is the normalized resonant frequency. And we have another simplified equation that we have obtained from the frequency domain specifications, that is resonant peak MR equal to 1 by 2 epsilon into square root 1 minus epsilon square. Here we have another equation. First equation is this is a function of u and epsilon. This is the magnitude is obtained as a function of u and epsilon. Similarly, magnitude or resonant peak will be obtained as a function of epsilon alone. See here MR equal to 1 by 2 epsilon into square root 1 minus epsilon square. Similarly, resonant frequency omega r equal to omega into square root 1 minus 2 epsilon square. These two equations we have obtained from the frequency domain specification. These are the final equation corresponding to the resonant peak and resonant frequency. And here we can relate the resonant peak with epsilon. Also we can relate resonant frequency with epsilon. In the previous case we have related the magnitude with the u and magnitude with and phase with u at certain values of epsilon. Here we are relating the resonant peak with the epsilon alone. So when we are taking epsilon equal to 0, when we are substituting that value, we will get omega r, that is resonant frequency, will be equal to omega n into square root 2 epsilon square. When we are substituting epsilon equal to 0, we will get that value equal to omega n. That means when epsilon equal to 0, resonant frequency will become omega n, will have a value of omega n. And when epsilon equal to 0, similarly we can substitute in this equation. We will get mr will be equal to infinity. When epsilon equal to 0, that means 1 by 0 equal to infinity. So these two are specific cases when epsilon equal to 0. We have discussed two other cases. And when epsilon equal to 0, these are the values corresponding to resonant peak. That means at epsilon equal to 0, mr will become infinity. So we can plot this as, see, when we are plotting mr, here is the mr with respect to epsilon at the point value 0, mr will have an infinity value. So we cannot mark it. So we will represent it as a point that is somewhere situating at an infinity. So it look like a straight line or going upwards, a line going upwards. Similarly, we know that here there are two equations, we can number the equation as 4.27 and 4.28. So we can say that when epsilon tends to 0, the resonant frequency approaches omega n and resonant peak approaches infinity. That is why we are drawing the curve like that. That is tending to going to infinity. Similarly, when 1 minus 2 epsilon square is equal to 0, that is another condition. 1 minus 2 epsilon square equal to 0 means epsilon will be equal to 1 by root 2. See here, 1 minus 2 epsilon square equal to 0 means epsilon square will be equal to 1 by 2 and epsilon will be equal to 1 by root 2. That is, its value is equal to 0.707. So when it will become like this, then omega r equal to, see, we have the equation of omega r equal to omega n into square root of this quantity, and this quantity equal to 0. That means omega r will become 0. That is, at epsilon equal to 1 by root 2, omega r becomes 0. So we have one condition, epsilon equal to 0, omega r equal to omega n. Similarly, when epsilon equal to 1 by root 2, omega r will become 0. So we can see that, we can say that for the range of values in between 0 and 1 by root 2, where 1 by root 2 equal to 0.707, in between 0 and 0.707, the resonant frequency always has a value less than omega n. See, for this value resonant frequency equal to 0, and for this value resonant frequency equal to omega n. So the resonant frequency has got a value omega n less than omega n between this range. Also we can find the value of resonant peak also. See, for resonant peak, when mr equal, we have an equation mr equal to this one, and when we are substituting epsilon equal to 0.707, there is some quantity here, and here also we can substitute 0.707. So the value of mr will be greater than 1 in that case. See, so we can say that the resonant peak has a value greater than 1 for epsilon equal to 0.707. So for epsilon greater than 1 by root 2, that is epsilon greater than 0.707, we can say that, see, this is the diagram, we can say that mr will be greater than 1. See here, you can see that at the limiting point of epsilon equal to 0.707, mr will be greater than 1, and also we have the equation for epsilon equal to 0, mr will be tending to infinity. So we can draw the curve like this. When we are taking different values of epsilon, we will get the different values of mr, and finally it will go from 1 to infinity. That is why we are drawing the curve here. Here we are not taking each and every values of epsilon. So we can say that for epsilon greater, next is epsilon greater than 1 by root 2. Here when we are taking epsilon greater than 1 by 2, the condition dm by du equal to 0 will not satisfied for any real values of omega. That is, for epsilon greater than 1 by 2, the magnitude m decreases monotonically from m equal to 1 at u equal to 0 with increasing u. See here, this is a previous curve and this is the curve relating m and u. In m and u, we can say that for epsilon greater than 1 by 2, the curve will monotonically decreasing. see, for different values of u, that is why it is saying that for epsilon greater than 1 by root 2, the magnitude m decreases monotonically from m equal to 1 at u equal to 0 with increasing u. That means it follows that for epsilon greater than 1 by root 2, there is no resonant peak and the greatest value of m equal to 1. So the frequency at which m has a value of 1 by root 2 is of special significance and is called a cutoff frequency, and which is indicated by omega c, and the signal frequencies above this cutoff frequencies are greatly attenuated on passing through the system. See, we have the equation for normalized bandwidth ub equal to omega b by omega n, and we have its value from the previous discussions as 1 by 2 epsilon square plus square root 2 minus 4 epsilon square plus epsilon raised to 4 all raised to 1 by 2. And this is the equation we have obtained from the resonant peak MR equations. That is the time domain specification. And similarly, so from this equation, we can find that ub is a function of epsilon. So first we draw the graph corresponding to m and u, and second we discussed about the relationship of m with respect to epsilon, and next we will correlate the u with the epsilon. So we are discussing this. So in this case, the equation for damped, so in this case ub, we can see that ub is purely a function of epsilon alone. That means when we are plotting m with respect to ub, actually it indicates that m, it shows the variation of m with respect to epsilon. Indirectly it shows that m varies with epsilon. So when we are drawing m with respect to u, it indicates that m will vary with respect to epsilon because u is a function of epsilon alone. That is why we are taking this equation for explanation. Similarly, now we have discussed about the case in the case of frequency domain specification. Now we have to discuss about the time domain specification. Actually, our topic is correlation between time domain specification and frequency domain specification. So we have discussed about frequency domain specification. Now we will say about the time domain specification, and here we know that in the case of time domain specifications, the expression for the damped frequency of oscillation omega d and peak overshoot, in that case in time domain specification we have represented the peak overshoot MP. Instead of MR we are representing MP, that is represents the maximum value, and we have the equation damped frequency omega d equal to omega n into square root 1 minus epsilon square. Similarly, peak overshoot MP equal to e raised to minus epsilon pi divided by square root 1 minus epsilon square. That you have studied MP and MP equation and omega d equations in the second module. And if we are comparing the equations of MR and MP, we can find that MR and MP are functions of epsilon. So MP peak overshoot is a function of epsilon. So we can plot a curve between MP and epsilon by giving different values of epsilon. So when we are plotting MP with respect to epsilon for different values, when epsilon equal to 0, see here when we are substituting epsilon equal to 0, we will get MP is equal to 1 value. So maximum value of MP is occurring at 1. So we have marked a point here. Similarly, when we are giving different values of epsilon, we will get different values of MP, and we can plot a graph between epsilon and MP. So we will get a curve like this. See, when MP equal epsilon equal to 1 by root 2 or 0.707, the MP will become 0. That means the curve will be looking like this. This is a curve for MP, and this is the curve for MR, and MR has a maximum value at infinity and MP has got a maximum value at 1. Similarly, here is a curve that is relating UB and epsilon, and here is the equation which is corresponding UB and epsilon. So we can draw the curve between this as like this. So when we are giving different values of epsilon, we will get the UB curve like this. Here if you are giving different values of epsilon, you will get a curve like this, but the substitution of epsilon for different values is not much important. That is why I am not discussing it. So these are the curves. So we can make a conclusion by using this. So figure shows the sketches of MR and MP corresponding to step input in the case of a second order system. So the system with a given value of MR, that means MR means resonant peak in the case of time frequency domain specification, that must exhibit a corresponding value of MP is subjected to a step input. That means for delta greater than 1 by 2, the resonant peak MR does not exist and the correlation breaks down. See here, when above 0.707, there is no value of MR. So there is no correlation between MP and MR. And the resonant peak MR does not exist for the values of epsilon greater than 1 by 2. So the correlation breaks down. And the comparison of the equation omega and omega d reveals that there exists a definite correlation between this omega r and omega d, where omega r is resonant frequency in the case of frequency domain and omega d is the damped frequency of oscillation in the case of time domain specification. Also there is a correlation between omega r and omega d, and the sketches of omega r and omega d with respect to epsilon is shown in the figure, and both omega r divided by omega d correlation is like this. So there is because omega r and omega d are functions of epsilon, both are correlated. That's all about this topic. Thank you.